Hello everyone, my name is Kaji Abramahman. Today we are going to talk about small signal model, especially hybrid pi model for BJT circuit analysis, and see some implementation for better understanding. What is a small signal model? Small signal model and why it is used, mathematics of some simplified small signal models, especially hybrid pi model, and finally we will see the practical implementation of CE amplifier for better understanding. Small signal model is a simplified linear representation of a BJT circuit. Usually a BJT circuit can get represented using a large signal Eber-Moller model, but it's a bit complex for computation, so a small signal variation of this model is used. The main assumption is the signal has a very small fluctuation. This is the DC value of the input signal and the fluctuation is comparatively small. This type of input signal can be analyzed through such simplified models. The model looks like an upside down pi, so usually it is called a hybrid pi model. Why small signal analysis? It's mainly due to the capability of linear approximating a small signal model, and frequency response analysis is also important for small signal models, especially to assess gain, bandwidth, and phase response. We can clearly see that small signal model can also be used to analyze the amplification characteristics of a BJT circuit, as can be seen from this picture. AC analysis is also an important aspect for these small signal models. So first let us observe how this small signal model can be used to analyze the amplification characteristics of BJT. For that we will use the voltage transfer characteristics, or VTC. VTC is the relationship between VBE and VCE on a circuit. Okay, this relation can be represented in this graph. As we can see in the active mode, the representation is very steep, and this steep nature can be used to build an amplifier circuit, especially in this linear region, and thus the necessity for a linear small signal model. So let us see the mathematics behind this small signal model so that we can have a deeper understanding. For that, first we know the branch current of IC can be represented in this exponential relationship where VBE is related to IC. We are using this relationship to expand upon. We will write E VBE. This is the DC component, VBE. This is the AC component, divided by VT. We will decompose it in AC/DC. Then we will use e to the power VBE by VT, the DC, and e to the power V small be by VT. This is the AC. This is a constant. These terms are very small due to the small nature of VBE fluctuation, so we can approximate it as EC1 plus VBE divided by VT. We can see the DC component and the AC component, and interestingly we can write the AC signal IC equal, we replace this with GMVB. This term GM is called the transconductance. Why it is called the transconductance? If we look closely, this conductive trans because it is IC divided by VT relates the voltage drop between VBE to the current of another branch IC, so it is mostly called a transconductive term. Now, if the amplifier is biased in active region, then we can write beta IB equal IC. Okay, we can see in this relationship beta divided by GM acts like a resistive component, so we represented it as RB VBE. Awesome. Now we have the value of IB, we have the value of IC. Okay, we know IE equal IB plus IC, so we actually have all the small signal values of a BJT. So the BJT that we already knew, an NPN transistor, this is B, this is C, and this is E, can be easily represented when it is applied a small signal as this is B, this is E. So we already knew that IB equal R pi VBE. So if this is IB and this is the voltage drop VBE, then this must be R pi. Okay, now similarly from previous analysis we had IC equal GM VBE. So if this is the C node and this is IC, then we can say that we can replace this branch with the voltage control current source with the value of GM VBA. Then we have IC, IB, and IE. So we can clearly see that we have represented our BJT with equivalent model when the input is a small signal. This equivalent model does not have any nonlinear characteristics, so it can be used for complex. Let us see a simple math example for this. For our AC analysis, we will ground all the source, meaning we will cut off all the source. This is a voltage source, so it will be grounded. Okay, and this will be shorted. Okay, now it will have, now in this branch we will replace it with our designed hybrid pi model. Okay, so it will be GMVBE. The values are not necessary for this example. We will have this, and this will be our small signal source. Okay, from here we will input our small signal V in. Okay, and this RC will be grounded like so, so it will be 1 kilo, and this is our VR. So this is the small signal representation of our CE amplifier circuit. It's interesting, but what will we do with it? There's an important aspect of it. We can easily calculate the R in, input resistance in from the input side, R out, output resistance in from the output side, and AV, the gain of the circuit, from this very circuitry. Okay, this will help us to design more complex communication system where the input and output resistance is very necessary. Now we will see a practical demonstration. DC bias it, we need to make sure that VC is half of the DC input voltage of 12 volts. We can say it's approximately 3 volts, so we need to change the variable resistance a bit and then try again. Finally, we have something of half of the input DC voltage. Okay, now we can apply the small signal. For that, we are using the computer and we're using 1 kHz sine tone, passing it through aux cable and then inputting it to the V-in of the circuit. Let us see what happens. Now we are going to see what is the waveform of this small signal. For that, we are going to attach a digital storage oscilloscope. Okay, now we shall see what is the input voltage looks like. We can clearly see it's a sine wave of something of 1 kHz. Now we are going to see the amplification of this wave. For that, we are now going to attach the second probe of the oscilloscope to the V out of our common emitter amplifier circuit. And now we are going to scale both of these probe inputs accordingly. You can clearly see after scaling, the yellow wave is our input and the blue wave is our output. We can clearly see a significant bump in output voltage, signifying that we have successfully built our CE amplifier. Another interesting characteristic of this circuit is its frequency dependency. Let us observe what happens when we input 10 kHz instead of 1 kHz. We can see the output waveform is severely distorted. This is because of the phenomena of Miller capacitance and the limitations of the circuit at high frequency. When frequency is increased, the gain of the CE amplifier decreases, which results in this output being cut off. We can reduce the effect of cutoff by reducing the input sinusoidal voltage amplitude. Let us see what happens. If we reduce it enough, we can see that we retain the sinusoidal output waveform. Finally, here are some mention that we will follow in the future, such as if we want to do complicated math, we can follow Sedra Microelectronics, and if we want to know in depth, so it's better to follow Robert L Boylestad electronic device and circuitry.